Welcome, everybody. Today we will start with section 5.3, which is all about concentration changes over time. Generally speaking, we are going to cover and how to determine the order of reaction using a method of a graph, and that's why it's changes over time. And section 5.2, we covered a method of initial rate, and from this method, we determine the order of reactions based on the initial concentrations. So how can I determine the order of reactions in terms of graphs, and how can I determine something called the half-life time? All right. The story starts once we made an experiment and determined the concentrations versus time for this experiment. And after that, we plotted the concentration versus time. Actually, it's done in here. After plotting concentration versus time, we just noticed that we got a straight line, okay, it's decreasing with a negative slope, as we can see. At this point, since we have a straight line, with a negative slope. Once we plotted the concentration on the y-axis and the time on the x-axis, I can deduce that the order is 0. In other case, after plotting the concentration with respect to time, for example, in here, we draw the concentration versus time, we just noticed that the line was not a straight line, it was like this. So at this point, since we do not have a straight line in this case, once we plot the concentration with respect to time, then we can say this reaction is not a zero order. So we have to try something else. All right. So I can say my reaction is not a zero order. I have to try something else. After trying the zero order and it didn't work, I have to try the first order. But how can I do this process? Since we plotted the concentration with time and it didn't work at that point, I have to say the y-axis must be changed. So in the first order, or let's say in our way to test the first order, we have to take the natural log of the concentration. For example, if the concentration is 0.025 molar, and if we take the natural log, which is for A here, we can say ln 0.025. So we can say the natural log actually represents the y-axis in your experiment, and the x-axis remains as it is, which is time. Now, if we have a straight line with a negative slope, when we plotted the natural log of the concentration versus time, then I can say my reaction at that point is a first order. So I can say everybody's happy and now it's ready. That's really good. But if you didn't have a straight line after plotting the natural log, let's say here A, with time, if you plotted this graph and for sure you didn't have the straight line, at that point you can say my reaction is not a first order. So we have to jump to the next option, which is a second order. So what should I do at this point? Let's erase the stuff. Now, since the concentration versus time didn't work, and then after taking the natural log of the concentration with respect to time and it didn't work, I have to choose the reciprocal of the concentration versus time. So generally, you have to take the reciprocal of your concentration. Your concentration was 0.025. The reciprocal is 1 over 0.025. And then you have to plot it. At that point, you can say the difference at that point here, which is the straight line that is increasing, and you can see that the slope is positive. So as long as you have a straight line with a positive slope, once we plotted the reciprocal of concentration versus time, then we can say the reaction is a second order. Okay. One more thing to discuss. The rate of reaction increases with increasing the concentration. And you have a higher pressure, then you could, for sure, you have high concentration. And if you have a high concentration, for sure you have higher absorbance of, absorbance and the UV spectroscopy. Okay. So we can say that it's okay to find a property on the y-axis rather than the concentration. So this property could be a pressure in here because it's almost the same as the concentration. If you have a concentrated solution, on the other hand, you can say high pressurized gas. It means a lot of particles. It's mean concentrated gas. So you could have a pressure on the y-axis and it happens. And you also have a rate on the y-axis and it happens because the rate is directly proportional to the concentration. And the same thing with absorbance. So any property that is directly proportional to the concentration can be plotted on the y-axis. So you just keep in this mind and do not panic if you see something else other than concentration. It could be rate, it could be pressure, it could be absorbance, all right, as long as they are proportional to the concentration. We have another thing to be discussed as well. The slope here represents the value of the rate constant, which is the proportionality constant. So from this plot, I can determine the order of the reactions in addition to determining the value of the rate constant. So we have like two benefits. In your AP exam, you'll be given this data booklet that contains pieces of information. So we can notice that the first equation is related the concentration versus time. If you just remember the straight line equations, it's just like A0. If you just rearrange these equations, you will have negative KT plus HE. At this point, you can see the coefficient of T is the slope here from your math skills. So we can consider the concentration. Here it's y, here it's the slope, the t represents x, and here it represents the intercept. This equation is used in order to determine the concentrations after a period of time. And since a node or A0 represents the initial concentration, here it represents the concentration after a period of time. So you can use this in order to determine, for example, the concentration after 10 minutes, 5 minutes, etc. And this is only for zero order. If you just remember the plotting of the concentration with respect to T, and we just got a straight line that is decreasing with a negative slope, and the negative slope is K, rate constant at that point. The same story is repeated in the second equation that represents the first order, and the same thing here is used for the second order. And for sure, I can determine the concentration after a period of time. And by the way, we'll apply some questions in this type of equations within the coming videos. So this is for the second order, this is for the first order, and this is for zero order, if you just remember the natural logs for those guys. All right. One more thing to discuss today, this magnitude T half, all right, is equal to 0.693 over K. And K for sure, it represents the proportionality constant as we learned. But this number comes from the natural log of 2. So what's the meaning of T half? T half tells me about the time needed to the initial concentration to be halved. For example, if we have a concentration, an initial concentration of 4 molar, and as a result or as the reaction proceeds, it becomes 2. So the time needed for this reaction to be halved in its concentration is called the T half. And keep in mind one more thing. For example, if the T half is, let's say, 1 minute, then it's going to be 1 minute here as well. But this sentence or this case is only for the first order reaction. So this law is applied only for the first order. This is only for the first order. And if you just look at the law of the half-life time for a first order reaction, like T half is equal to 0.693 over K, we can notice that the time is only dependent on the value of the rate of reaction. And if you just remember that the rate of reactions depends only on the temperature. So if you want to decrease the half-life time, you're supposed supposed to increase the value of K. Increasing the value of K means increasing the temperature. And that's why, if you just remember, if we increase the temperature of reaction, the reaction becomes faster. And if it becomes faster, it takes less time to proceed. So this is another thing that you have to keep in mind. One of the most famous reactions that are always a first order, the radioactive decay. The radioactive decay, for example, if you have iodine 131, this is a radioactive atom or an element, and it has a first order reaction because it's always first order. Okay, so if we just have a look at this point, as we said, the T half for a first order reactions are always fixed, which means if you just have a look at this, since here we have a pressure on the y-axis, okay, with respect to time, so we can see that we started with 150. The half of 150 is 75. So there's a time needed for the 150 to jump to 75, which is closest to 14,000 seconds. And for the 75 to be halved, it takes time as well. And we can see that it's almost like if we take the difference between here and here, it's almost about 28,000, and it's also 14,000 seconds. We can see that the T half is equal in both sides. It's 4,000 seconds. It may change, depends on the type of reactions, and depends on how it proceeds. All right, now let's practice what we covered so far. Let's take an example. Question says here, what can you conclude from the fact that the plot of natural log of a pressure versus T is a linear? Since it's a pressure with respect to time and it's not a straight line, then I can say it's not a zero order, and I excluded from my options. But since we took the natural log with respect to time and we got a straight line decreasing negative slope, we can say this is a first order reaction. This question, as we can see, we are given, and this question is concentration and time, and the question is asking me, is this a first or a second order? Since it's asking me whether it's a first or a second, then the zero order is excluded from our calculations or from our considerations. So I have to take for the first order, like try it, we have to try this. In order to test it in the first order, we have to take the natural log and plot this column versus time. And after that, we just noticed that the curve looks like this, and it's not a straight line. So I can say this reaction is not a first order. So I have to try another thing by taking the reciprocal of concentration with respect to time. And as we can see, drawing the reciprocal of concentration versus time, we got a straight line with a positive slope, and that's why I can say this is a second order reaction. Let's practice this question. The question says, at 600 Kelvin, this compound will decompose to form sulfur dioxide in chlorine gas via the above equation. If the reaction is found to be the first order for overall, a first order, just like keep in mind, which of the following will cause an increase in the half-life time? So first order has a lifetime of this. So we can notice that the half-life time is not affected by any concentration, but it's affected by temperature. So the question is asking me which of the following will increase the half-life time. So I need this to be increased. Okay, so A says increasing the initial, no, it's independent of the concentration. B, increasing the temperature at which the reaction occurs. If we increase the temperature, the K will increase, and as the K increase, the T half will decrease. So it's not an answer. C says decreasing the overall pressure In other words, it's concentration, it's independent of pressure, it's independent of concentration. So none of these will increase the half. Yes, this is the answer. So the D is the answer. At that point, I hope you enjoyed the lesson. If you have any questions, you can ask me in the comments below or you can send me my emails. Thank you.